Okay, good afternoon, everyone. It is my distinct pleasure to introduce Gauri Joshi, who's going to give us a very exciting talk on computational heterogeneity in federated learning systems. Gauri is an assistant professor in the EC department of Carnegie Mellon University, and he is one of those people that really list a lot of different awards, and most notable among them are her NSF Career Award, Sigmatic Best Paper Award, and then also NSF CRII Award in 2018, among others. So we are really looking forward to her talk today, and without further ado, I'll just turn it over to her, and I guess people have a little bit of time after the talk to ask other questions as well. Gauri, thank you very much again, and please take it away.
Thank you so much for the introduction and for organizing the talk. So I'm excited to present this work on tackling computational heterogeneity in federated learning. This is joint work with several collaborators, but it's mostly led by two PhD students of mine, Jianyu Wang and Yeji Cho. So in this talk, I'm going to first give you a brief overview of federated learning for those who may not be familiar. It is an emerging machine learning paradigm where training of models can be done on resource-constrained edge devices, which is very well aligned with the theme of the institute. A key challenge in federated learning is heterogeneity, both in terms of data that is collected by these devices, as well as their computational capabilities. So in this talk, I'm going to talk about two works related to computational heterogeneity. Firstly, in terms of devices having different computation speeds, and secondly, in terms of the intermittent availability of these edge devices. So that's the plan for the talk. Let me begin by talking a little bit about SGD, because when I say designing algorithms for distributed or federated learning, what I really mean is stochastic gradient descent, because machine learning training today is synonymous with using SGD. It's the most common optimization algorithm. At its core, it's very simple. It involves optimizing an objective function such as this, which is also called the empirical risk minimization function. And in every iteration of SGD, we update the model parameters, which are represented by X over here, by computing a gradient on a small batch of samples chosen from this N samples of the training data set, and computing gradients for those samples and taking a small step in that direction of the gradient. So as you can see from this update equation, SGD is inherently sequential. But for large data sets, performing SGD at a single node can be prohibitively slow. So we have to come up with a way to distribute SGD across multiple nodes. And that is why most standard implementations of SGD are in the form of distributed SGD. In the data center setting, this is also called the parameter server framework, which is used for distributed training of machine learning models. So in this framework, you have a parameter server, which stores the current version of the model. The model contains, say, the weights and biases of a neural network, or if it's not a neural network, any other parameters that might be there that we want to tune. And then you have a system of workers, M workers in this case, which store different partitions of the data set. Since the training data set is really large, it is shuffled and then equally partitioned across these worker nodes. And then in each iteration, the algorithm proceeds as follows. These workers, they will read the current version of the model from the parameter server. Then they will compute gradients on one mini batch each. And then the parameter server will collect all of these gradients, average them, and then update the global model. So this is the standard algorithm, which is also called synchronous distributed SGD. And there have been several works on improving the scalability of this framework. So you can, by looking at this picture, you can probably already guess scalability issues such as synchronization delays or straggling delays, communication delays, etc. And many works, including some works from my group, have looked at removing the synchronization barriers or reducing communication in different ways to improve the scalability of this framework. So in spite of all of these works that improve the scalability, this parameter server framework still has some key limitations. So the first thing is that it assumes that these workers are homogeneous and that they are available throughout the training process. And secondly, more importantly, this framework assumes that there is a centrally available data set which can be shuffled and evenly partitioned across the worker nodes. And these assumptions, especially the second assumption, fails in many emerging applications where massive amounts of data is being collected at edge devices, such as cell phones, tablets, sensors, etc. So an example is the next word prediction service that most of us have on our smartphone keyboards, where as we type text, there is a language model that predicts the next word that user may type. Now, in order to train these models, if we naively use the parameter server framework, we would have to send all the data to the cloud for the purpose of training. So everything that a user types will have to be sent to the cloud. And firstly, sending raw data can be expensive when these devices are bandwidth limited and they have high latency on their communication links. And secondly, it also may violate privacy laws, which prevent data sharing with foreign cloud servers. So to address these two issues of communication limitations and privacy constraints, this framework called federated learning has become very popular in the past 4 or 5 years. It operates within these constraints by using the core idea that we don't move the data from the devices to the cloud. The data stays on the device. And instead, we perform model training to the edge, because now these edge devices have some computation capabilities, however limited, and these computation capabilities can be used to do a few rounds of machine learning training in order to only share model updates with the cloud rather than data. So the basic idea of federated learning is that it's divided into communication rounds. And in each round, an edge client takes the current global model, performs a few local updates based on its local data set, and then sends these updates back to the server, which will aggregate and update the global model. So this framework, because it keeps the data on the device, it provides better communication efficiency and privacy guarantees than sending raw data to the cloud. Right. So if you look at this picture that I've shown here for federated learning, it may seem very similar to the parameter server framework picture that I showed a couple of slides ago. And one might think, wouldn't the same algorithms work in this scenario? So it is true that these frameworks are similar, but they have some subtle yet important differences. The first major difference between data center based and federated training is that here data are highly heterogeneous across the devices, both in terms of size and composition. Whereas in the parameter server framework, we had a central data set that was shuffled and equally partitioned. So the data was largely homogeneous across the worker nodes. Secondly, the computation speeds of these clients can vary widely. And these are not just short-term fluctuations in speed that may occur in cloud, but they can be consistent long-term differences between different devices. So for example, if one of these devices is a phone, another is a sensor, another is a tablet, all of them have quite different computation speeds. And the next thing is that due to communication limitations, these clients have to perform multiple local updates. They cannot just do one gradient computation and send the gradients back to the central server. That would require too much frequent communication with the parameter server or the central server. So the communication has to be infrequent and efficient. The next thing is that the scale of the system is just much larger. Here you can have thousands or even millions of geo-distributed edge devices, whereas in the cloud, we have maybe tens or hundreds of these worker nodes. And lastly, because of the scale of the system, only a subset of these clients are available for training at a given time. Right? So these are the main differences between federated learning and data center based training. So I hope that gives you a good high level idea of what is federated learning and the challenges. So now let me be more concrete and define the objective function and put it in context of the goal of this talk. In federated learning, because each edge device has their own local data set, we can define a local objective function, phi of x, which is the average of the sample losses for the points in the local data set. The local data set is denoted by di. And then the global objective function, which we seek to minimize, is a weighted average of these local objectives, where the weights are proportional to the size of the data at the ith client. Why do we choose as weights proportional to the size of data? The reason is that we want to emulate the data center based centralized training framework where suppose we collected all the data at a central location, then each data point will have equal weight, and then each local objective will have a weight proportional to the data set size. So here, although we are not collecting the data together, we design the objective function in such a way that it emulates centralized training. So the goal of federated learning is to minimize this objective function and find a global model X that works well for this global objective and hence many of the local objective functions. So note that there are other works in federated learning that modify this objective, where they consider personalized models that are customized to each client. But for the purpose of this talk, I'm going to focus on just having one single global model that will be used by all the clients in the system. So that's the goal. And by looking at these definitions, you can already see that depending upon these local data sets, these local and global objectives can be very different from each other. And that can affect the conversions and consistency of the solution. So to minimize that objective function, the basic algorithm that is used in federated learning, which is called Fed averaging, does the following. So it starts off with the central server sending the current model to all these clients. Then these clients will perform tau local steps of SGD using their own data. And because these data are heterogeneous across the clients, the models that they will end up with are different from each other. These updated models are then aggregated by the central server in proportion of the size of the local data set. So the new model is equal to a weighted average of these updated models. So the question that we want to answer in this work is, how does this algorithm operate, or how does it work in terms of, in the presence of data and computational heterogeneity? So the outline of the rest of my talk is going to be first talking about the effect of data heterogeneity on the performance of this algorithm. That is, how does the choice of the number of local updates and how different the data sets are across the clients, how does that affect convergence? And then later I will go to talking about computational heterogeneity of two forms, which is the main focus. So the first part, I'll spend a little less time on it because there's a lot of work in this area, which people may be already familiar with. And the purpose of this section is mainly to give you intuition about how tau affects convergence. So let me pause here quickly in case there are any questions. Okay, so let me go to the first part where we'll look at how the number of local steps tau affects both the speed of conversions in terms of error as well as in terms of runtime. So first thing that you can see is as we increase tau, we are performing more local computation and less frequent communication with the central server. So communication efficiency will certainly improve as we increase the value of tau. And this is because for the same number of communication rounds, we will perform many more iterations if you have larger tau. So this is easy to see. The other side of the story, besides just purely the number of iterations that we will complete within a given number of rounds, is how good are these iterations and how well do they perform the task of achieving the minimum of the objective function. So let's look at the quality of the solution and how it is affected by tau. To understand it, let's consider a toy example where there are just two clients, and we are going to consider two extreme cases. One is tau equal to 1 and the other is large tau. So in this picture, what I'm showing is this black dot, which is the current version of the global model. And X1 star and X2 star, these triangles, they show the local minimum of each of the two clients. And X star is the global minimum. So we want the global model to minimize the global objective function. That's why we wanted to reach X star. If tau is equal to 1, that is each client just does one local update, then the algorithm will proceed as follows. In each round, a client will do one local step, and this step will roughly be in the direction of its own local minimum. And then we will average these resulting models and update the global model. So the global model will now move in this direction of the dotted blue arrow. And if we proceed similarly, eventually we can show that if we follow the trajectory of this global model, it will converge to X star, which is the global minimum, assuming it's a unique global minimum. So if we have a non-convex objective function, we can show that it will converge to a stationary point of that objective function. But the trajectory of this global model, in general, it will be equivalent to the trajectory that will be taken by the model in synchronous SGD. So there's no problem with consistency or quality of the solution here. But now let's look at the other extreme case. What if tau is large? That is, each client does many local updates rather than just one. If they do that, then each client will reach close to its own local minimum. And this may seem good because when we average these, we'll end up with this global model, which seems to be making swift progress towards the global optimum X star. But in reality, it gets stuck somewhere around this point. And that's because once the global model is updated, in the next round, these clients will again do many local updates, and they will again go back towards their own local optima. And when we average, we'll come back to this point. So there will be this gap between X star and the point that we converge to. So the takeaway message from this is that doing too many local updates, while it's good for communication efficiency, it can be bad in terms of convergence because it will lead to an inconsistent solution that differs from the global optimum. And we can formalize this by analyzing the convergence in terms of tau. And we can show that if we use a decaying learning rate, then there is one term that decreases with tau and another term that increases with tau. So there's this trade-off between communication efficiency and error convergence. And the training loss for large tau, it's drops sharply at the beginning of training because you do more iterations in the same number of rounds. But later on, because of this solution being inconsistent, you get a larger error flow. So how do we strike a balance between these extremes? Some ideas that have been proposed include just setting a small or moderate value of tau, or choosing a small enough learning rate so that these clients' models do not drift far away from each other. Another solution is to pull back the client's models, stopping them from drifting away. Both of these solutions work, but then they will slow down the conversions. So another strategy could be to adaptively change tau. So we start off with a large value of tau and then gradually decrease it as we come closer to convergence. So these are some of the strategies that are used to address data heterogeneity. For the most part, as long as you control tau and control the learning rate, the problem of data heterogeneity can be tackled using these strategies. However, computational heterogeneity is something that is not studied enough, and it can also lead to serious convergence issues that are harder to address. So in the rest of the talk, I'll talk about computational heterogeneity. The first work that I will present is on the case where these devices have different speeds or they even use different local optimizers. So why would they do that? Why would devices do different numbers of local updates? That's because depending upon how you implement the federated averaging algorithm, inherently these devices might end up doing different numbers of local updates. So let me show some examples of that. The first thing is that when I described the Fed averaging algorithm to you a few slides ago, I said that each client does the same number of local updates tau. But in many practical implementations, the clients actually do the same number of local epochs, not updates. And an epoch means an entire traversal of the local data set. And because the size of the data is different across the clients, what will happen is that clients with more data will end up doing more local updates in this version of the algorithm. And as a result, there will be this heterogeneity in the number of local updates across the clients. Another case where heterogeneity can occur is in straggler resilient versions of Fed averaging. So suppose we want to make Fed averaging straggler resilient such that we don't have to wait for the slowest client to finish tau local updates. What we could do is we can fix a time window and then allow clients to do as many local updates as they can within that time window. In this way, faster clients will do more local updates, slower clients will do less local updates, and then we aggregate these updates. And another source of heterogeneity besides these two, even if, let's say, we fix the number of local updates across the clients, they may be using different local optimizers. So if they use things like local momentum or proximal local updates, or maybe different learning rates or adaptive optimizers. So all of these will lead to heterogeneous local progress. And although these sources of computational heterogeneity are known, the current implementations disregard these for the most part, and they just naively aggregate the client's updates. And such naive aggregation, while ignoring computational heterogeneity, can be pretty bad for conversions. So to see that, let's look at a toy example again with the two clients with these local optima and the global optima being here. So if we start off with the global model X, and let's consider the homogeneous setting where these clients do the same number of local updates, then our global model moves in this direction as illustrated in the figure. On the other hand, if these clients do different numbers of local updates, let's say the client 1 does 5 local updates while the client 2 only does 1 local update, if we naively aggregate them, then the global model will be skewed towards the first client. And then this skew or this bias cannot be fixed easily using the techniques that are used to tackle data heterogeneity, such as choosing small eta or small tau. So this kind of skew can lead to the global model just being inconsistent with the global objective function. So to understand the convergence properties in this heterogeneous setting and come up with a way to fix this skew, in our work, we came up with a generalized version of the Fed averaging algorithm. And then we analyzed the convergence of that algorithm and then proposed a method to fix this inconsistency problem. So in this analysis, one key takeaway was that if we consider the homogeneous setting, then the algorithm is effectively trying to minimize the actual global objective, the true global objective, which is the weighted sum of local objectives in proportion of the dataset sizes. Whereas in this heterogeneous setting, the vanilla Fed averaging algorithm ends up optimizing a mismatched objective. So instead of this global objective, it ends up optimizing this function where the weight now increases with the value of tau I. And this mismatched objective can be arbitrarily different from the global objective. So how do we resolve this discrepancy, and how do we make sure that the algorithm optimizes this objective and not this one, but it still allows clients to do heterogeneous number of local updates? So to understand that, let me first describe to you the generalized version of Fed averaging, which allows different local updates, and then show the convergence analysis of that in order to see how we can fix this problem. So this is the original Fed averaging update rule written in a slightly different form, where these deltas show the model update locally done at each client. So at each client, it starts off with this global model, does local updates, gets this local model. The difference between these two is denoted by delta. The delta is effectively a sum of all of these local gradients multiplied by negative of the learning rate. So we generalize this update rule in two ways. The first thing is that instead of the delta or the local accumulated local update being just the sum of these local gradients, let us allow it to be any arbitrarily linear combination of these local gradients. So now you have these coefficients AI that determine how, in what proportion these gradients are mixed together. And the advantage of this generalized version is that depending on how we set these coefficients or AI, the generalized algorithm can capture different local optimizers. So for example, FedProx corresponds to AI being equal to this. Momentum SGD done locally would correspond to AI being equal to this. So this is the first generalization. The second generalization is that instead of the central server taking an average of just delta i's in proportion of pi's, we allow it to take a weighted average of normalized local changes. So by normalized, what I mean is that this accumulated local gradient, we divide it by the L1 norm of that AI vector, and we use this normalized vector in place of the capital delta I. And finally, we allow this averaging weight to be any arbitrary weight Wi rather than fixing it as Pi, which is the fraction of the data set at the ith client. So the normalized update rule, putting all of this together, looks as follows. We have the normalized gradient, which is the accumulated update normalized by the coefficients of that EI vector. And the normalized gradient is determined by the choice of the local optimizers, such as vanilla SGD, FedProx, momentum SGD, etc. The second aspect of this generalized algorithm is the aggregation weights, which are used to average these green color arrows or the normalized gradients. And these weights determine the direction of this averaged update shown in the orange arrow. And finally, you have another parameter here, which is called the effective steps per round, which decides the magnitude of the averaged update. So by setting these three parameters to different values, now we can capture several existing algorithms. And for this generalized update rule, we can show that if we use this update rule, we will end up optimizing an objective function, which is given by this, which is a weighted sum of the local objectives, but now in proportion of Wi, which are the aggregation weights that are chosen by the algorithm. Now, Fed averaging is a special case of this algorithm where all the AIs are set to 1 over TI, the WIs are set to this, and tau effective is set to this. And because it is, it chooses Wi as this and not equal to Pi, that is why the surrogate objective for Fed averaging is actually mismatching with the actual objective function. So this analysis actually leads us to a quick fix to this aggregation problem. All we have to do is change these aggregation weights from this value to just Wi equal to Pi. And by just doing that small change, we can ensure consistency of the solution with respect to the true global objective function. So let me illustrate what I mean by that. This new algorithm, which fixes these aggregation weights, is called FedNova, or Federated Normalized Averaging. And what it does is that instead of the regular Fed averaging update rule, which averages these local updates in proportion of Pi, it takes the accumulated local update and divides it by the number of local steps that we take. So since we are taking 4 local steps here, we divide it by 4 and get this green color arrow. Here we are taking 2 local steps, so we divide it by 2 and get this second green color arrow. And then we average these normalized gradients. And you might think, does this slow the algorithm down because now you're reducing the magnitude of these arrows? It doesn't slow it down because we can adjust that tau effective parameter to rescale the magnitude such that it matches with the expected magnitude in the original case. So the FedNova update rule looks similar to this, except it's taking normalized accumulated gradients here, and then it's setting this tau effective parameter so as to rescale the update. And this modified update rule will optimize the correct objective function. And that's how we can ensure consistent convergence. I think I'll go over this more quickly. We also have a convergence analysis of that generalized federated averaging algorithm. We can show that the error after T rounds is like this. The first term is a vanishing error term, which is standard, similar to previous analysis. The second term, which is a non-vanishing term, it comes from data and computational heterogeneity. So it is 0 only if there is either if there is no data heterogeneity, that is this kappa parameter, which captures data heterogeneity is equal to 0, or it is 0 if the aggregation weights are set correctly to PI such that this term goes to 0. So this analysis framework is interesting because it gives a convergence guarantee for existing algorithms such as FedProx and others, whichever are subsumed within that generalized framework. And let me also quickly show you some experimental results. So these are comparing Fed averaging with the normalized averaging method FedNova. And we can see that as compared to Fed averaging, which converges to a suboptimal solution, because FedNova fixes those aggregation weights in the correct way, it gives fast conversions. And what we can see is that FedNova is also compatible with different local solvers. So you can use any local client optimizer and only fix the way in which the updates are aggregated. So by doing that fix, we can get almost, in some cases, 8 to 10% accuracy improvement. And finally, I talked about the clients doing different numbers of local updates. As I mentioned earlier, they might also use different local optimizers. And although current implementations use vanilla SGD as the local optimizer, if we use something like Adagrad or Adam, we can get much faster conversions to the local optima in each round. But these adaptive methods have not been used at the client side. They're only currently used on the server side. And that's because they also lead to this inconsistency problem, because the adaptive local progress depends on local Hessians. It can lead to heterogeneous progress across the clients. So it is illustrated by this figure. The blue color line shows federated averaging. The green color line shows the case where you change the local optimizer at the client to Adagrad. So we can see that initially it gives this sharp drop in error, which is good because Adagrad gives fast conversions to the local optimum value, but then it settles with a high error flow. And this is because of the progress being heterogeneous across the clients. And this is what is causing the solution bias. So inspired by FedNova, we can build a similar method to correct for this bias and get both the benefits of Adagrad or Adam without having these problems of solution bias. So we cannot directly apply the FedNova framework here because in the FedNova framework, the normalized update is a linear combination of these local gradients. Whereas in adaptive methods, it actually corresponds to multiplying the local grade, each sequence, each gradient in that sequence by a preconditioning matrix and then taking an average of these. So this is a generalization of the linear combination update. So we can account for this by generalizing FedNova and changing the way in which we aggregate gradients and apply this correction. So in this generalized version, each client will have to do some local correction in order to compensate for heterogeneity in their local progress. And then the server will have to apply a global correction when it aggregates the updates from all the clients. So I won't go into the details here and maybe leave it for offline discussions. Let me pause again to see if there are any questions.
So Gauri, I guess my question was in the chat. I can see that having, selecting weights in an appropriate way could kind of help with this normalization. I was just wondering, is it reasonable to assume that you would have this information to create the appropriate weight in your distributed federated learning setting?
I see. So your question is that we are setting the correct weights, but do we have the information that is necessary to choose the correct weights? So the information that we need is just the number of local updates that each client does. In order to do that normalization, which I showed earlier, that's all we need. And the second thing we need is the fraction of data at each client. So, and these two parameters are generally known to the central server. It doesn't need a lot of additional information. That said, here in this generalized version with adaptive optimizers, we do need a lot more information because these clients have to send matrices, these correction matrices, and not just their accumulated local update. So there is some additional communication in this case, but in the earlier version of FedNova, there's not much additional communication or information that we need.
I see. Thanks.
Thank you. So I think there's one more question.
I have another question, if possible.
Go ahead.
Hi. So still regarding to these ways that have to be selected, depending on the training strategy. Have you thought with your group to maybe actually learn these parameters also as part of the learning process? Meaning that that they could be, they look like hyperparameters, the way you describe them, but maybe they can also be somehow learned during the training process. I don't know if you see my point.
I see. Yeah, so there are three things here, right? These are the way you aggregate, and then the way you normalize, and these effective steps per round. The first two, they are known, so we don't really have to learn them. As long as we know the number of local steps that each client does, we can appropriately choose these parameters. But the third one is a hyperparameter. So this controls like something analogous to a global learning rate. And that one we'll have to tune it using a validation data set. So we haven't looked at them as parameters that we train because these are more like hyperparameters that we would have to tune using some validation data.
I see. So this basically also depends on the type of training and model
Yeah,
amount
so
of
these
data you have.
first two things actually, they depend on the system parameters, like how fast a client is.
I see.
So once you know that, once you know how many local updates it can do in that round, we can just directly choose these.
Okay. All right. Thank you.
Sure. Any other questions?
I have a question.
Mm-hmm.
Actually, I understood that the heterogeneity exists for data
Mm-hmm.
between the agents, but on the other hand, the learning framework, like weights in the deep learning or the number of layers and nodes, like the learning framework for each agent and that for global agent should be identical here.
Oh, okay. So your question is, in data heterogeneity, like what does it mean? Does it mean that the model architecture is different across the clients or the server? So the answer is no. In the Fed averaging framework that I described, the same model with the same number of layers, neurons per layer, etc., is replicated at all the clients. And what is changing is the training data distribution. So the training data would consist of samples which have features and labels, and that will be different across different clients.
So data generation, distribution, or something else are different between the agents.
Yes, exactly. But the model is.
By the way,
Mhm.
in order to sum over the axes, I think the format, the dimension of the X should be the same for all agents, shouldn't it?
Yes, that's right. So the dimension is the same. So X contains the parameters of the model.
So model
Like
should
the
be the
number of
same.
weights and number of biases, and because the same model is used at all the agents, the dimension is the same.
Okay, I understand.
Yeah, so there's
Yeah.
actually some recent work on model heterogeneity as well. I'm not talking about that here, but some papers have looked at cases where agents or clients can use different models. But then
Yes.
while aggregating them, we cannot just average them like what I'm showing here. You would have to do some kind of distillation of these models into the global model.
By the way, this is not related to this research. I have one more question.
Mm-hmm.
Is there any recent works that considers the error probability between the single agent and the global agent?
Mm-hmm.
Between them, we need to communicate the X values because the global agent should average the axis. So, but I think in the wireless system, there will be the error probability between communicating between the agents. So is there any papers?
Oh, I see. So I think
that?
what you're asking is communicating this X can be noisy.
Yes, right.
Right. So yeah. So in fact, in order to save the communication cost, there are existing works that propose ways to quantize or sparsify this vector. If it's a high dimensional vector, you want to send a compressed version of it, which will also introduce error on top of the error coming from the communication channel. And this error, if it's small enough, it doesn't affect the conversions that much because these updates are already stochastic updates. So there's several sources of noise. There's already noise coming from the stochasticity of the gradients. Then there might be noise coming from quantization, sparsification, or also from the communication channel. Generally, SGD is pretty robust to these noise sources.
Okay, I understand. Okay, thank you.
Sure. Thanks for the questions.
Hi, Professor Joshi.
Mm-hmm.
I have one question. First of all, thank you for the talk. So my question is related to the communication complexity issue. So by
allowing these local updates, does the communication complexity improve compared to not allowing local updates?
Okay, so I think it depends on how you define communication complexity. So if you say that one round counts as one communication cost,
yes, yeah, that's
one
my
unit
understanding.
of communication cost, then it does improve, because now in each communication round, you do many local updates. So there's faster progress towards the optimum value.
So for example, then in terms of that communication cost definition, is there a complexity analysis that shows how much it improves compared to not allowing local updates? For example, how much larger tau may improve this?
Yeah, I think so. The question that you're asking has been like puzzling researchers in federated learning for the past few years. Let me go back. I think I have some time. So I showed this convergence analysis several slides ago. Here, so there are these two terms in the error. One of them reduces with tau, another increases with tau. So there is a trade-off between both of these. And a combination of both these terms will affect the overall convergence. So it's not always good to increase the number of local updates, because the second term can go up.
Okay.
Yeah. So I think that there is also, so this convergence bound, for many years it has been of this form, but I think there is some room to improving this. And the second term is somewhat pessimistic. It shows that it increases with tau, but in some cases it might not increase with tau, which means that doing local updates is even better.
I see. Thank you.
Yeah, there are some interesting open questions around this convergence question. Right, thanks for all the questions. I think in the remaining few minutes, I'll go over the third part of my talk. I'll be happy to take more questions offline if we run out of time. So the last part is going to be about intermittent client availability. So as I mentioned earlier, because we have thousands or millions of these edge clients, it's not feasible for all of them to participate in every training round. So in every training round, we select a subset of these clients and then use those to update the global model. So this subset will induce a surrogate objective, which will be the sum of the local objectives of the selected clients. And typically the selection of the client subset is done in an unbiased manner. And because of unbiased selection, most of the prior results that are derived for the full client participation setting can also apply and extend to unbiased client participation. But the question that we wanted to answer here is it always good to do unbiased client selection? Can we actually gain something by doing biased selection of clients? So to illustrate this, let's look at a toy example with two clients whose objectives functions are shown in blue and green. And then the red color function shows the global objective function. So if we do unbiased random selection, let's say we choose only one client per round, then every time we choose that client, we move down along that function. And then we might switch back and forth between the functions. So in this example, we might move downwards along the screen function. And then if we choose the other client, we switch over to that function and then move down along that function. And this is how the switching back and forth occurs. But our goal is to optimize the red color function, which is the global objective. And that may not work very well with unbiased selection, because there might be cases where you keep on circling around, oscillating between optimizing the first function and the second function. In expectation, we will optimize the red color function, but it might take much longer to get there. On the other hand, suppose we preferentially select clients that have high local losses, then in this case, we will, because the green function is higher than the blue color function, we will keep on going downwards along the green function. And only at this point, we will switch over to the blue function. So you can see that here in just 5 iterations, we were able to come close to the minimum of the global function, which is red. So I hope this example gives you some intuition. The main message here is that biasing the selection towards higher loss clients could give us faster conversions. But then will this lead to some skew that will affect the quality of the solution? So that's the problem that we wanted to understand in this work. So we came up with a framework to consider the selection skew in the convergence analysis. I'm going to skip this slide in interest of time, but the main takeaway message is that there is this selection skew parameter rho, which increases if we bias towards higher loss clients, and it decreases if we bias towards lower loss clients. And if it is unbiased selection, then this is just equal to 1. And then we can get a convergence analysis in terms of this selection skew parameter, which shows that the rate of convergence can improve with selection bias, but it might lead to a slight increase in the error floor. So inspired by this, we came up with an algorithm which we call power of D choices in client selection. It's inspired by power of D load balancing, which is used in scheduling. This algorithm, the way it selects clients is that first it selects a candidate set of clients, which is of size D. And then among these, it computes their local losses and then selects the clients which have the highest value of local loss. So you're kind of sampling some set randomly and then biasing towards higher loss clients among them. So by controlling the value of D relative to M, we can go all the way from unbiased client selection to fully biased client selection. So this idea is also connected to importance sampling techniques that are used in single node SGD, where you select samples not uniformly at random, but in proportion of the local sample losses. So we observed that this framework, by just selecting D that is a little bit higher than the M that we want, we can get faster conversions than just unbiased random selection. So increasing D gives faster conversions, but it may lead to a slightly higher solution bias. So in order to compensate for that, and in order to compensate also for the computation cost of step 2, we can come up with efficient versions of this algorithm, as well as some adaptive versions of this algorithm that give a better convergence guarantees. So in this plot, I'm showing random selection versus power of D choices, and 2 versions of it that are more efficient and practical. And we can see that as compared to random selection, these algorithms can give a higher test accuracy and lower training loss. And this gap actually increases with data heterogeneity. So if you have more data heterogeneity, doing biased client selection can be even better. So that was all for the talk. So I hope this gave you a good flavor of the problems in federated learning and the new challenges. So I covered the first 3 challenges listed here, but there are several others that are interesting, such as personalization, fairness, robustness, etc. So I'll leave you finally with the links to some of the papers that were covered in this talk and other papers that are related but not covered in the talk. Thank you everyone for your attention. I'll be happy to take any questions.
Thank you very much, Gauri. It was a very interesting and very informative talk. I personally, have a lot more appreciation for all the different types of questions that really come up in this realm, and hopefully once I digest them a little more, I'll have more questions. But in the meantime, if others have any questions, please feel free to chime in, and in the remaining couple of minutes, maybe we can try to get at least a glimpse of an answer for them.
I think people asked several questions
earlier. Yeah, there were several questions like dispersed throughout the talk, which was great. I mean, I really enjoyed that kind of interaction too. Again, thank you very much, Gauri. Thanks for your time. Thanks for the great presentation, and we will definitely be in touch. And thanks you everyone for being here today, attending this talk. Hopefully we will have more interesting talks coming up. We are scheduling them, and we'll be announcing them as we go along. Again, thanks, Gauri, for today's talk, and everyone have a very nice day, and we'll be in touch again.
Thanks.
Bye. Thanks for the invitation. Bye.